Problems are solved with the help of one or the other search techniques. Hence, search technique forms a core component of many intelligent processes. Search is a systematic approach to find a path from a root state to the goal state. There are many traditional search algorithms exist. With the help of these algorithms, we can solve many of the artificial intelligence applications. But there are some applications which needs a sophisticated search algorithms. Hence, we use heuristic functions to design such algorithms. Before we understand the different search algorithms, first we will try to understand the requirements to be satisfied by a search algorithm. There are mainly two requirements an search algorithm should satisfy. The first one is it should cause a motion. That is, whenever you apply an algorithm, we should be able to move from one state to another state. The second one is the algorithm should be a systematic. That is, it should have a step-by-step approach so that we can move from the source state to the goal state in this case. Now coming back to the different type of search algorithms in artificial intelligence. The first one is uninformed search, also called as a blind search. Second one is called as informed search, also called as heuristic search algorithm. First we will try to understand uninformed search algorithm. In uninformed search algorithm, given a state, if you have multiple number of paths, it will not select a path which is having a least cost, or you can say that the optimal path. It will go to each and every path, and then it will try to get the goal state over here. For example, in this case, let us say that right now we are present in this state A. There are two paths are there. Either we can go to this particular B, and then we can go to this particular C to reach this particular goal state G here. So in uninformed search technique, it doesn't apply any logic or something like that. It will choose one of this particular thing, and then it will try to go to this particular goal state over here. So if it goes through this particular path, let us say that A to B, B to D, D to C, and C to G, it will be a lengthiest path over here. But if it has gone to this particular side, that is A to C and C to G, it would be the least cost path in this particular case. But it will not apply any logic here, and then and it will just follow up one of this particular path, and then it will try to reach this particular goal state over here. So that is the reason it is called as uninformed search technique. Now coming back to the second one, that is called as informed search, or it's also called as heuristic search. So whenever you are present in a particular state, and there are multiple paths are there from that particular state, it will use some heuristic function, and then based on that particular thing it will make a decision, should I choose the first path or should I choose the second path. So that is what the main thing happens in this informed search technique. So just to understand, let us assume that right now we are present in this particular state. Yes, there are two paths are there. Either we can choose this particular path to go to this particular A, or towards this particular path we can select so that we can reach this particular D. For this one we have the cost 3, and for this one we have cost 4. Now there are multiple informed search algorithms are there. Just to explain this particular informed search technique, I will consider A star algorithm. So what A star algorithm does is, it will take this particular cost plus it will consider the heuristic value. This one is called as a heuristic value, that is 10.1. What is this 10.1 is? It is a probable distance to reach from A to goal state here. Now if you add these two things, that is 3 plus 10.1, it will become 13.1. So that is the heuristic value of this particular path. Similarly, we need to calculate, so at this particular point of time, this will be the better option over here. A suitable path so that it can reach this particular goal state with a minimal cost over here. So this is how the informed search algorithm works. I have discussed this particular algorithm in detail in another video. We just go through that particular video to understand the completely how A star search algorithm works. Now these particular algorithms, that is informed and uninformed search algorithms, were again categorized into multiple number of algorithms. Uninformed search techniques were divided into three groups mainly. One is called as depth first search algorithm. If the implementation is done with the help of LIFO, that is stack. Second one is a breadth first search algorithm. If the implementation is done with the help of queue or FIFO. If priority queue is used, such kind of algorithm is called as a cost first search algorithm in this case. Again, this depth first search algorithm is divided into two things based on the depth limit. Whenever you set the depth, for example, depth is equal to 2 or something like that, it will become a depth limit search over here. Again, if you go on increasing that particular depth from 2 to 3, 3 to 4 or something like that, it will become iterative deepening depth first search algorithm over here. So these are some of the different algorithms which comes under this particular uninformed search. Coming back to informed search algorithm, they were categorized into mainly three groups. First one is generate and test. Second one is hill climbing. Third one is divided again into. Hi, welcome back. In this video, I will discuss breadth first search algorithm in artificial intelligence with a very simple solved example. First, we will see what is the algorithm or how it works, and then we will take a very simple example. In the first step of the algorithm, we need to create a node list, and then we need to set the node list with the initial state. That is nothing but we want to go from initial state to goal state. So the initial state will be put into node list in the first step. And then until the goal state is found, we need to repeat this particular second step. Or there is another possibility, if you don't find the goal list, it may happen that the node list will become empty. So if a node list becomes empty, the meaning is we haven't reached that particular goal state, or the path is not found till the goal state. So that is the meaning of the node list is empty. So either of these conditions should satisfy. Until that condition gets satisfied, we have to repeat this particular steps here. Now what we do is we will remove the first element from the node list. We call it as E. E. That is the first possibility. If there are no elements in the node list, what we say is we say that the goal is not reached, and then we will quit this particular algorithm, or you can say process, you can say. So first we will try to remove an element from the node list. If it is available, we will call it as E. If there are no elements in the node list, or you can say that the node list is empty, we will quit this particular algorithm here. Now, if there is an element in the node list, we will do the following with respect to the element E in this case. So first we will apply a rule to generate the new state. That is nothing but we will try to get the successors of that particular E here. If the new state is a goal state, we will quit and then return this state. Otherwise, add the new state to the end of that particular node list. So unless and until we reach the goal list, or you can say goal node, we have to repeat this particular step here. So we do one thing. We'll take a very simple example to understand this particular algorithm. So this is the graph given to us. In this case, A is the can say that initial node, and G is the goal node in this case. We have multiple goal nodes in this case. We have 1, 2, 3, and 4. Either of these goal nodes has to be reached. If you reach that particular goal node, we have to stop it. If you haven't, or if you are unable to reach that particular goal node, we will say that it's a failure in that case. So first we will start with the initial node. That is, the initial node is A. That we will put into a node list. Initially the node list contains only the initial node, that is A here. Now what we do is we will remove this particular element from the node list, that is A, and then we will find the successors of A. The successors of A are B and C. So we will put B and C into node list in this case. So now the node list will look something like this. Now from this particular B and C, we will select the first one, that is B, and then we will find the successors of B here. The successors of B are D and E. So we remove this, D and E will be added into this particular node list here. Now it looks something like this. B has been reached. D and E are the successors. We haven't reached these things. We have just got the successors of B in this case. Now, from the available elements from the node list, C is the first one. So we will try to do what? We will try to find the successors of C. Now we will try to find the successors of C. D and G are the successors. We will add these two nodes into this particular node list, and C will be removed here. So this is how actually the node list will look like. After this, D is the first node from this particular node list, so we will get it, and then its successor C and F will be added here. So this is how actually the node list will look like. From this particular node list, we will get the E. E does not have any successors, so once we reach the node, F will be added here. Node from this particular node list, so we will get it, and then its successor C and F will be added here. So this is how actually the node list will look like. From this particular node list, we will get the E. E does not have any successors, so once we reach this particular E, we don't have any successors here. So we have left with only D, G, C, F. Those are the only 4 nodes in this case. Now we will try to find the successors of D here. B and F are the successors. So we will add those two things into this node list, and D will be removed here. So this is how the node list will look like. Finally, G is the element, or the first element from this node list. We will try to find the successors of G here. We don't have any successors, that's the first thing. The second thing is that G is the goal node. So because we have reached the goal node, we say that the algorithm has ended successfully. Finally, we will give the path, or we can say that the final path to reach the goal node. In this case, the final path is from A to C, and then C to G in this case. So this is a very simple example to understand how breadth first search algorithm works. The breadth first search algorithm works, what you can say that the breadth-wise. It will try to get the successors of node. It does the same thing level by level, unless and until we reach the goal state in this case. Now we will try to understand the advantages and disadvantages of breadth first search algorithm. The advantages of BFS algorithm are, this is one of the simplest search strategy in artificial intelligence. BFS is a complete, that is, if there is a solution, BFS is guaranteed to find that particular solution. If there is no solution, it cannot find it, but if there is a solution, it will definitely find that particular, that's for sure. If there are multiple solutions, then minimal solution will be found using BFS, that's for sure. For example, in the previous case, we were having multiple number of goal nodes, so definitely we must be having multiple number of paths to reach that particular goal node. So in such case, this algorithm will definitely return the minimal solution, or you can say the minimal cost path in that case. Now we will see some of the disadvantages of BFS. The breadth first search algorithm cannot be effectively used unless the search space is quite small. Because what happens is, if the goal node is present at the leftmost at the exponential depth, what we need to do is we need to traverse each and every node or a level, then only we can reach that particular goal node. So definitely it will take the lot of space. So that is the one disadvantage of BFS algorithm. In this video, I have discussed what is the breadth first search algorithm and how it works with a.
Welcome back.
Welcome back. In this video, I will discuss how to solve 8 puzzle problem using breadth first search algorithm, that is BFS, in artificial intelligence. In the previous videos, I have discussed what is BFS search algorithm, and I have solved examples using BFS search algorithm. Link for those videos is given in the description below. In this case, we have been given the initial state as well as the goal state. What we need to do is we need to apply the BFS search algorithm on the initial state until we reach the goal state here. So first we will define what are the possible moves we can perform. We can move this blank in 4 directions, that is left, up, right, as well as the below or the bottom here. So these are the 4 possible moves we can perform on a given state here. But at a given point of time, we may not be able to apply all these 4 moves, because at this particular point of time, you can see here, this particular blank can move to the left side, up and the right. The bottom move is not possible at this point of time. So that is the one thing we need to remember here. So we will start with the initial state. We will try to apply the BFS until we reach this goal state. So in BFS, first we will see whether initial state is a goal state or not. If you compare initial with the goal state, it is not a goal state here. So what we need to do is we need to perform the different possible moves here. So in this case, we can perform 3 moves. That is, we can move this blank to the left side, up, or the right side here. So once you perform all these possibilities, we will get 3 new states here. So once you get the 3 new states, we need to compare these states with respect to the goal state. If any one of these is the goal state, we need to stop here. So right now, all these states are not equivalent with the goal states. So what we need to do is we need to expand these states in this case. So in breadth first search algorithm, once you expand the root node, we need to expand the all successors of the root node here. So here we need to expand this one. Now if you want to expand it, we need to check what are the possible moves we can perform here. Again, this blank can be moved up or the right side here. These are the only 2 possibilities. But if I move to the right side, what will happen is we will get the initial state only. So this is not suitable here. And when it comes to this state, we can move this blank in 4 directions. But if I move this blank to the bottom, again we are getting the initial state here. So that's the reason that is also not suitable. We can move this blank to the left side, up side, and the right side here. These are the 3 possibilities. Similarly, for this one, we can move this blank to the left side as well as the up here. But if I move to the left side, again we are getting the initial state, so that is not suitable. Only thing is we can move this blank to the upper side here. So once you perform it, you will get these states in this case. Now again, whenever you get a new state, what we need to do? We need to compare against the goal state. If there is a match, we need to stop over there. Now whenever you see here 5, 6, 7, 8 or 9th state, none of them are equivalent with this one. So we need to start expanding it over here. Now we will start with the state number 5 here. Again, when you look at this state number 5, we can move this blank, that is upper side, right side, and the bottom here. Now if I move it on the bottom side, again we are going to get the its parent here, so there is no use of doing that one. So there are only 2 possibilities. We can move this blank to the upper side or the right side here. We will get, these are the 2 possibilities, that is 10 and 11 here. Again, none of these 2 things are equivalent to the goal state, so we will go to the next one. Now we will try to expand this 6 here. Again, we can perform 3 possibilities. Out of that, moving this blank to the right hand side is not suitable, because we will get the same state of parent. So there are 2 possibilities. Either we can move up or bottom here. We will get these 2 states in this case. Now when you come to the next state, 7th, again there are 3 possibilities are there. But if I move to the bottom, again we are going to get the parent here, so there is no use. We can move either left or right. We will get these 2 states here. The same thing we need to perform on all possibilities here. And whenever you get a new state, we need to compare against the goal state. If there is a match, we need to stop over there. Now if you look at all these states, none of them are equivalent to the goal state, so we need to start performing the BFS again here. Now we will start with the leftmost state here. When you look at the leftmost state, there are 2 possibilities are there. Either we can move this blank to the right side or the bottom. But if I move on the bottom, again we are going to get the parent here, so there is no use of it. So we will get only 1 state here. So that is what we can notice here, that is 20. For this one, there are 4 possibilities are there. But out of 4 possibilities, moving this blank to the left hand side is not suitable, because we are going to get the parent here. The remaining 3 are well and good. This whole state, you can see here, if I move this blank to the right side, rather than expect of BFS search algorithm is clear at this particular state. Welcome back. In this video, I will discuss depth first search algorithm with a simple solved example. Also, I will discuss what are the advantages and disadvantages of DFS algorithm. So first we will see the depth first search algorithm. In the first step, we will check whether the initial state is the goal state. That is, we want to go from initial state to goal state. If the initial state is already a goal state, what we do is we will quit and then we will return as a success. Otherwise, we will do the following steps unless and until we reach either the success or the failure is signaled. What we do is we will generate a successor E of the initial state. So we have initial state, we will find the successor of that particular initial state and we will say it as E. If we don't have any successor, the meaning is we have not reached the goal state, so we will return the failure in this case. If we have a successor, that is E, what we do is we will call this particular depth first search algorithm with E as the initial state now. So previously initial state is the first state. We got the successor of that particular initial state, that is E. Now E has become the initial state. Until and unless we reach that particular goal state, we go on calling this particular depth first search recursively in this manner. If the success is written, the meaning is we have reached the goal state. Otherwise, what we do is we will return this particular thing again and again over here. Now we will take a very simple example to understand this DFS algorithm. So this is the graph given to us where A is the initial state, G is the goal state. We have multiple number of goal states here. Now we will take a very simple example to understand this DFS algorithm. So this is the graph given to us where A is the initial state, G is the goal state. We have multiple number of goal states here. You can find 1, 2, 3 and 4 goal states here. So initially what we do is we will put this initial state, that is A, into the node list. Now we will try to find the successors of A, that is B and C. So A is removed from node list, B and C will be added here. Now once you add B and C, what we do here is we will get the first successor, that is B here. Now this B will become the initial node here. Because B is the initial node, what we do, we will check whether initial node is a goal node or not. Because B is not a goal node, what we do here is we will find the successors of B here. What are the successors of B? The successors of B are D and E. So what we do, we will add D and E into this particular node list by removing this particular B here. Now this node list will look DEC here. Again, we will take the first element from this particular node list, that is D. We will check whether D is a goal node. D is not a goal node. Hence, what we do is we will remove it from node list and then we will add the successors of D into the node list at its place, that is C and F. Now it looks what we do, we will add D and E into this particular node list by removing this particular B here. Now this node list will look DEC here. Again, we will take the first element from this particular node list, that is D. We will check whether D is a goal node. D is not a goal node. Hence, what we do is we will remove it from node list, and then we will add the successors of D into the node list at its place, that is C and F. Now it looks something like this: CF, EC. Now again, we will take the first element from the node list, that is C. C is not a goal node, so we'll get the successors of C, that is G here. So we will remove this particular C. At the place of C, we will put G here. Now it will become something like this. Again, we will get the first element from the node list, that is G. We will check whether G is the goal node. Because G is the initial node right now, we will check whether it is a goal node also. Because G and goal node are one another same, the meaning is we have reached the goal node in this case. And the path to be followed is A to B, B to D, D to C, and C to G in this case. So this is what the process we need to follow in a DFS algorithm, so that we can go from initial state to goal state in this case. Now we will see some of the advantages and disadvantages of DFS algorithm. The advantages of DFS algorithm are: the DFS search requires less memory since only the nodes on the current path are stored. You just see here in this case, what has happened is, whenever we go from A to G on this particular path, whatever the nodes are there, only they were what we can say that saved into the memory. But if you see the BFS algorithm, what actually happens is, uh, if the goal node is present here, we should reach each and every node before this particular level. For example, if the goal node is present on this level, we have to reach all these particular nodes, then only we can reach this particular goal node here. So that was the disadvantage of BFS algorithm. But in DFS, we will reach only those nodes which are present on the current path, you can say. So that is the one advantage. Because of that, it needs less memory here. The depth first search may find solutions without examining much of the search space at all. Again, the same thing, because we found this particular G without visiting many of these particular, what you can say that the states here. So that's an advantage of DFS algorithm over BFS algorithm. But it does have disadvantages. The first disadvantage is, we may find, we can say that suboptimal solution using DFS algorithm. The meaning of this one is, whatever the path we find, we may get it is the deepest, can say that the path, or most more costly path, you can say. In this case only, again you can see here, the path from A to G is A to B, B to G, because we have to cross. Actually, if you see this particular side, is this, and the cost will be definitely more, because we have to cross 4 nodes so that we can reach this particular goal node or state here. But actually, if you see this particular side, A to C, C to G is actually the one more goal node we have here. So this is the best solution, because it finds, what we can say that the nodes on the current path, we have to go from A to G. If we don't have anything, then we have to go to the next one, then next one, then next one. So the advantage is, it needs a minimum memory, but the disadvantage is, it will give you suboptimal solution in this case. The second one is, it's incomplete. The meaning of this one is, without a depth bound, one may not find the solution even if it exists. So that's a one more problem. BFS is a complete because it will find the solution if there is a solution. I hope this video will help you for your exam. There are other Welcome back. In this video, I will discuss uniform cost search algorithm in artificial intelligence with the help of simple solved example. Uniform cost search algorithm is an uninformed search algorithm in artificial intelligence. There are other uninformed search algorithms in artificial intelligence like TFS and BFS. I have already discussed those algorithms and the link for those videos is given in the description below. Uniform cost search algorithm uses the lowest cumulative cost to find the path from the source node to the goal node. That is, first we need to find the cumulative cost of each and every path. The one which is having the lowest, that will be considered as the optimal path in this case. We will start expanding the root node until we will get the minimum path. In this video, I will discuss uniform cost search algorithm in artificial intelligence with the help of simple solved example. Uniform cost search algorithm is an uninformed search algorithm in artificial intelligence. There are other uninformed search algorithms in artificial intelligence like TFS and BFS. I have already discussed those algorithms and the link for those videos is given in the description below. Uniform cost search algorithm uses the lowest cumulative cost to find the path from the source node to the goal node. That is, first we need to find the cumulative cost of each and every path. The one which is having the lowest, that will be considered as the optimal path in this case. We will start expanding the root node until we will get the minimum cumulative cost to reach that particular goal node. The uniform cost search algorithm is implemented with the help of priority queue over here. Following is the process we will use to get the optimal path in uniform cost search algorithm. That is, first we will insert the root node into the priority queue. From that particular priority queue, we will remove an element with the highest priority. At the initial stage, we will be having only the root node, so we will need to remove that particular thing. But after a certain period of time, we may be having more than one node into that particular priority queue. So we will need to remove an element or a node with the highest priority at that particular point of time. Now, whatever the element or the node we have removed, we need to check whether it is a goal node or not. If it is a goal node, we need to stop the algorithm and then we need to print the total cost here. Otherwise, we need to add all the children of the current node to the priority queue with their cumulative cost from the root node as the priority. And then we need to add this particular current node, the one which is removed from the priority queue, as the visited node in this case. Now we will take a very simple example to understand this particular algorithm. Let us assume that this is the graph given to us and this is the source node and this is the destination node. Now what we do here is we will start exploring this particular tree or a graph from this particular source node. So first we will explore this particular source. Because this is the only thing present in the priority queue, we will try to expand it. As it is not a goal node, we will expand it and we will get A, B, C as the three possible nodes in this case. All these particular things will be added to the priority queue with the cost as the priority in this case. Now out of these particular three, A is having the minimum cost, so we will consider it as the node with the highest priority. So we will try to explore this particular A now. Now when you explore this particular A, there is only one path you can see here, that is G. That is what I have written in this particular case. And the total cost to this particular G is 1 plus 3, that is equivalent to 4 over here. Now we have G, B and C on this particular priority queue. Out of these three, B is having the minimum cost. So from B we have only one path, that is B to F. So that is what we will explore here. Now the value of this particular F is equivalent to 3 plus 5, that is equivalent to 8 in this case. Now at this particular point of time, G, F and C are present on the priority queue. Out of these three, G is having the minimum cost here. But if you look at this particular G, from G we don't have any other nodes. So we will say that from here onwards we cannot explore. We will remove this particular thing from the priority queue, and then we will consider other nodes over here. So the other nodes on the priority queue are C and F. Between these two, C is having the minimum cost, so we will try to explore it. So when you go to this particular C, we have only one path, that is C to E, with 2 as the cost. So the value of this particular E will become 5 plus 2, that will be 7 in this case. Now between E and F on this particular priority queue, we have the value of E is less in this case, so we will consider E. From E, we will go to this particular destination with cost 1, and the total cost of this particular destination is equivalent to 5 plus 2, that is 7, 7 plus 1, which is equivalent to 8 in this case. Now we have reached this particular goal node, so we will stop this particular algorithm, and the path to reach this particular goal node is source to C, C to E, E to destination, and the total cost is equivalent to 8 in this particular case. This is how we can apply the uniform cost search algorithm to the given
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem combination sum 2 from the SDE sheet. But before moving on to the problem, if you guys are new to our channel, please do consider subscribing to our channel. So the problem states that you'll be given a collection of candidate numbers and you'll also be given a target number. And your task will be to find all the unique combinations in that array candidates where the candidates do sum up to the given target. Now there are something that you need to take care of. Each number in the candidates can only be used once while making the combination. The next stuff is the solution set must not contain duplicate combinations. So you can see that this is the given candidates array, which is 10, 1, 2, 7, 6, 1, 5, and the target is given as 8. So one of the possible combinations can be 1, 1, 6. The other possible combination can be 1, 2, 5. So what you need to return is basically everything in the sorted order, and whatever combinations you are getting, all of them should be in the lexicographical sorted order, and you need to return them. So you can see there is a combination 1, 2, 5. So either I pick this one, then I pick this 2, then I pick can only be used once while making the combination. The next stuff is the solution set must not contain duplicate combinations. So you can see that this is the given candidates array, which is 10, 1, 2, 7, 6, 1, 5, and the target is given as 8. So one of the possible combinations can be 116. The other possible combination can be 125. So what you need to return is basically everything in the sorted order, and whatever combinations you are getting, all of them should be in the lexicographical sorted order, and you need to return them. So you can see there is a combination 1, 2, 5. So either I pick this one, then I pick this 2, then I pick this 5. So I will get a 1 to 5, or either I pick this one and then this 2 and then this 5. This can be also another 1 to 5, but if there are multiple combinations, you can just pick once. So that is the problem. So for this example, if you're asked to find the target equal to 4, the combinations will be 1, 1, 2, and the other combination will be 2, 2. Now you cannot say 1, 2, 1 as a combination. That is not valid because all the combinations should be in the sorted order. So once they are in the sorted order, you will only get these two combinations, and this is what you need to return. Now again, this one, and this two can form a 1, 1, 2, or this one, and this two can form a 1, 1, 2, but it doesn't matter. You just need to return the one combination that gives 1, 1, 2, no duplicate combination. So this problem is basically the second version of the combination sum. So to solve this problem, the brute force that we will be following will be inspired by the part 1 of the combination sum. So let's discuss the brute force. If you want to understand the brute force, it's mandatory that before starting off with this explanation, you should have seen the combination sum 1 video that I have already made. So if you haven't seen it, pause this video, go and check it out, and then you can come back. If you have seen that video, you remember that we were allowed to pick an element once. So that is why when we pick the element from index, we always move to the index because we can pick the element once more. And whenever there was the other case of not picking, we can move to the next, that is index plus 1. So the transitions were like this in combination sum 1. But in this combination sum 2, the question states that we cannot pick an element more than once. So if you're picking the element, will you stay at the same index? Obviously not. You will move to the next index that will make the state as index plus 1. That will make the state as index plus 1. And that is the only change that you need to do in order to get all the combination that does give you the sum target. From index, you just need to move to index plus 1, because once you have picked the index and once you have called this recursion, after this, that hash set can be converted, yes, can be converted to a list of list, and then you can return this list, then return the list. So this will become something like hash set. I'm just writing a set as of now. So this can become a set. So if you add it to the set, so it will make sure that duplicate combinations are not stored. So if you remember, so if you are staying at the same,
Welcome back. In this video, I will discuss how to apply uniform cost search algorithm to find an optimal path. This is the solved example number 2. I have already discussed what find an optimal path. This is the solved example number 2. I have already discussed what is uniform cost search algorithm and what are the different steps in uniform cost search algorithm. Also, I have solved a numerical example using uniform cost search algorithm. Link for those videos is given in the description below. In this case, we have been given a graph with multiple number of nodes. Here C is the root node, Z and G are the goal nodes in this case. In uniform cost search algorithm, we will set the cost is equal to 0 initially and open list is set to the root node here. Now what we need to do is we need to remove this node from the open list and then we need to explore the root node here. So I will remove C from the open list and then I will find the possible paths here. There are multiple paths are there. There is one path from C to B, another path is from C to D, C to T, C to O, C to E and C to P here. For each of them there will be some different cost here. So I will add all those possible paths into open list here. The meaning of B2 is to reach B from C, the cost is equal to 2 here. Similarly, other paths were added into open list here. Now, once you add all these possible paths, we need to sort these paths according to the cost here. Once I sort it, I will be getting T1 as the first place, B2 as the second place, and so on. Now, the meaning of this one is we have explored the root node. Now, we need to select the first node from this open list and then we need to explore it. So, the first node from this open list is a T. I will select a T. The meaning is I will remove T from open list and then I will add all possible paths from T into this open list. We don't have anything from T here, so we don't add anything, but we have removed a T from the open list here. Now we haven't reached the goal node, so we need to look for the other possibilities. The next possibility is B2, that is B is the next node. We will remove it from the open list and then we will explore B here. There are three possible paths are there, A, R, S. To reach this particular A, we need the total cost is equal to 3. To reach this particular R, we have the total cost is equal to 2 plus 4, which is equal to 6, and so on. We will add all those paths into open list in the ascending order here. Now, once it is done, we haven't reached this goal node yet. So we will select the first node from this open list again, that is E2. And then we will remove it from the open list and then we will explore E here. Once I explore E, the cost to reach this G is equal to 2 plus 5, that is 7, that is added into open list here. Now, again, we haven't reached this goal node. So we will take the first element from the open list, that is O3. Once I explore the given graph to find the optimal cost from root the cost. Welcome back. In this video, I will discuss iterative deepening depth first search algorithm in artificial. artificial intelligence with a simple numerical example. This is the modified version of depth limited search algorithm, which is again a modified version of depth first search algorithm in artificial intelligence. I have discussed both depth first search algorithm as well as depth limited search algorithm in the previous videos. Link for those videos is given in the description below. To understand iterative deep link depth first search algorithm, first we will try to understand depth first search algorithm briefly. In DFS algorithm, we will start at the root node and then we will try to traverse the left side of that particular tree, and then if we get the root goal node, we will stop over there. Otherwise, we will try to search the right side of that particular tree. The same process will be continued unless and until we will get the goal node here. So
Remember the time complexity discussion that we did while solving the combination sum 1, we did find it as 2 to the power n into k. And this k was because you're putting a data structure into another data structure. But now the time taken will be k log n. Why will that be? Because you're putting a data structure k that will take a length k, and you're putting it into a set now. So that's going to take an extra log n. So I can say if you follow this method, the time complexity of brute force will be 2 to the power n into k into logarithmic of something, that is the set size. So since the interviewer will not like that extra logarithmic factor, we will have to remove it. And for that, we have to modify our recursion in a bit different way. So let's see how are we going to do that. So this time, instead of trying pick and non-pick, we are going to try to pick subsequences. Yes. So let's see how we are going to start off with. So imagine you have a function. Okay. So assume you're starting with the 0th index and you have a target of 4 that you need to make, and you have an empty data structure. So if I ask you, can you start with this 0th index? Your answer will be yes. Can you start with the first index? Again, your answer will be yes. Can you start with the second index? Your answer again will be yes. Can you start with the third index? Yes. Can you start with the fourth index? Yes. Now, when I say start, what does that mean? That means if you start with this 0th index, you are getting the first element of your combination as 1. Assume after that you decided to pick this third index, you get a 2. And after that you decided to pick this fourth index, you again get a 2. So probably you can decide to pick a combination in this way. So whenever I am starting with the 0th index, I can pick the 0th index. There can be a possibility. Or I can pick the first index. Again, there can be a possibility of picking up the first index. I can also pick the second index. And similarly, I can also pick the third index. And again, going by, I can also pick the fourth index. So these are the 5 possibilities that I can pick up as the first element. Now let me ask you one thing. If you're thinking of picking someone as your first element, so even if you pick the 0th index guy as the first element, or the first index guy as the first element, or the second index guy as the first element, will that matter? Obviously not. If you're picking 0th, first, second, doesn't matter. You're ultimately picking 1 as your first element of the combinations. So this is where you have your trick, which makes sure that duplicate combinations are not picked while recursion. Now you will understand this as I start writing the recursion tree in depth. So I decided to pick the 0th index, which will mean that since I've picked the 0th index, I will move to the first index, and my target, which was 4, will now be reduced to be 3, and my data structure will have an element 1. Now I will not perform this recursion. Similarly, I will not perform this recursion because I've already started with someone who is starting with 1. So there's no point starting with these guys again. That will give me repeated combinations. Now for the third index, can I pick 2 as the starting element? Obviously I can. So if I pick it up, my data structure will obviously have the element 2. What about my target? If I'm picking someone which is a value 2, my target will get reduced by a value 2. Hence, it will be reduced to 2. What about the index? Now remember one thing. You require all the combinations in the sorted order. Like the combination must be like 1 comma 1 comma 2, not 2 comma 1 comma 1. So make sure whatever array is given to you, you sort it, and after that you start preparing combinations by recursion so that you only get the combinations in sorted order. So if you have picked up 2 and you're looking for a sorted combination, you are not going to pick up anything from the left. Obviously, so you will decide to pick up anything from the left. Obviously, comma 1 comma 1. So make sure whatever array is given to you, you sort it, and after that you start preparing combinations by recursion so that you only get the combinations in sorted order. So if you have picked up 2 and you're looking for a sorted combination, you are not going to pick up anything from the left. Obviously, so you will decide to pick elements from the right. So that means you'll move to the 4th index. That is very obvious because if you have picked the 3rd index guy as the first element, the next elements will be picked from the right. Now, will you pick the 4th index as your starting element again? Obviously not, because you already have picked someone which is a value 2, which is your starting index. So I will decide that I am not going to pick. So this guy will not be picked. So as of now, yes, as of now, we have these 2 recursion calls which will be made. And at first, this recursion call will be executed, and after that this. So let's execute this portion. So what if you're standing at the first index and there's this target tree you have to make? So again, you have an option of either picking this guy, either picking this guy, either picking this guy, or either picking this guy as your second element of that combination. Because when you say your data structure has 1, you're looking for the second element. So I can say I can either pick the first index, I can either pick the second index, or I can either pick the third index, or I can again either pick the 4th index. You have 4 options open to you. Who can be your second element. So if I decide to pick the first guy, again, understand, if you are wanting to pick the first index guy as your second element, that means you have picked the first index. So you will obviously move to the next index, that is 2. And what about your target? Your target is going to reduce by 1. So your target will be 2 now. And data structure will have something as 1, 1. So you have something like this. Now, can you pick the second index? Obviously not, because if you have once picked 1 and 1, so the combination is going something in this direction. And then you decide to pick the second index again into this. That's again going to give you the same combination, right? So we want to avoid duplicates. So this we will not pick because this guy is first. So second, we're going to pick someone once only, not more than once. So keep that in mind. Now, the fourth index, you have, I can either pick the first index, I can either pick the second index, or I can either pick the third index, or I can again either pick the fourth index. You have 4 options open to you who can be your second element. So if I decide to pick the first guy, again, understand, if you are wanting to pick the first index guy as your second element, that means you have picked the first index. So you will obviously move to the next index, that is 2. And what about your target? Your target is going to reduce by 1. So your target will be 2 now. And data structure will have something as 1, 1. So you have something like this. Now, can you pick the second index? Obviously not, because if you have once picked 1 and 1, so the combination is going something in this direction. And then you decide to pick the second index again into this. That's again going to give you the same combination, right? So we want to avoid duplicates. So this we will not pick because this guy is first. So second, we're going to pick someone once only, not more than once. So keep that in mind. Now, will you pick the third index as your second element? The third index has an element 2. So I will decide that, okay, let's pick that. So if you're picking this 2 out, where will you move? You have picked the third index. So obviously, if you have picked the third index, the next picking will begin from the fourth index and your target will be reduced by 2. So the target will be left off with 1 and your data structure will now have 1 and 2. That means first element is 1, second element is 2. That's your combination till now. Now will you pick the fourth index? That's the question. Again, no, because you have once picked 2 as your second element. Now, again, if you pick the fourth index, 2 will be picked as your second element and we don't want that. So we will avoid doing it. So again, there are 2 recursion calls and we know that the left recursion call does get executed at first. So what we do is we execute this. Now we are at the second index. So we are looking for the third element to be picked. So again, the second index can be picked up, the third index can be picked up, the fourth index can be picked up. There can be 3 options. Now, can we pick the second index as our third element? Yes. If we pick it up, our combination will take the shape of something like this. And a function, if you have picked up the second index, now we'll look for the next index, that is the third. and the target will be reduced by 1 because we picked up 1 and it stays as 1, and the data structure this time will be 1 1 and 1. Now can you pick the third index? That's the question. Yes, because you have a 1 comma 1 as your first couple of elements. If you pick the third index, that's gonna make it 1 comma 1 comma 2. So what I decide is, okay, let's go and pick the third index. And if you're picking the third index, you cannot pick it more than once. So you move to the next index, that is 4. And what about your target? Your target this time from 2, since you have picked up 2, becomes 0, and your data structure is gonna have a 1 1 2. Similarly, will you pick the fourth index? No, because if you pick the fourth index, you're again gonna get the same combination. So this is why if there are consecutive elements which are same, like there are a couple of 2's, we just decide to pick the first 2 and we ignore the other 2's which are on the right for a third element that we are picking, or for any index element that we are trying to pick. So we don't pick it. So this is how we can avoid multiple same combinations. I hope you have understood this. Now there are a couple of recursion calls on this level, and we know that the left recursion call will be executed at first. So if you have the third index and you have a data structure which has 1 1 comma 1, so you're actually looking for someone on the fourth as the fourth element. So can you pick up the third index, or can you pick up the fourth index? Let's see. If you are wanting to pick up this 2, you'll not be able to pick up because your target value is 1, and at the third index the value is 2. So you cannot pick up. So you cannot pick up this, and similarly you cannot pick up the fourth index. So what we see is we have a target value which is lesser than the array elements, and we know anything on the right of these guys are always going to be greater than target. So what we do is we no further call recursions and we stop, and this able to pick up because your target value is 1, and at the third index the value is 2. So you cannot pick up. So you cannot pick up this, and similarly you cannot pick up the fourth index. So what we see is we have a target value which is lesser than the array elements, and we know anything on the right of these guys are always going to be greater than target. So what we do is we no further call recursions and we stop, and this combination can never be a valid one. So this recursion call is over, and it did not give us a valid combination. But what about this? You reached target 0. So whenever you reach your target 0 and the recursion was called, you can actually think this as a base case, that whenever the target 0 recursion is called, that means the data structure is carrying the combination which has given you the target 0. So you can say 1 comma 1 comma 2 is your first combination that you got using this recursion. Now similarly, you have done this, so you go back. So this complete recursion call is done. Now you're left off with this recursion call, and you can again try out the fourth index, and you'll not be able to pick up anything because on the fourth index there is a 2 and your target value is 1. So again this recursion call will also not be a valid recursion call. So you cannot call this recursion as the target is lesser than the array index that you're calling for. So this recursion call is over. So now you come across to this recursion call which is left out to be executed. So you're currently at the fourth index and you have a target that is 2 which is left out. So your data structure has two. So it's looking for a second element, and you're at the fourth index. So you can pick up the fourth index. So the fourth index has a 2. And if you are wanting to pick up this 2, you'll not be able to pick up because your target value is 1, and at the third index the value is 2. So you cannot pick up. So you cannot pick up this, and similarly you cannot pick up the fourth index. So what we see is we have a target value which is lesser than the array elements, and we know anything on the right of these guys are always going to be greater than target. So what we do is we no further call recursions and we stop, and this combination can never be a valid one. So this recursion call is over, and it did not give us a valid combination. But what about this? You reached target 0. So whenever you reach your target 0 and the recursion was called, you can actually think this as a base case, that whenever the target 0 recursion is called, that means the data structure is carrying the combination which has given you the target 0. So you can say 1 comma 1 comma 2 is your first combination that you got using this recursion. Now similarly, you have done this, so you go back. So this complete recursion call is done. Now you're left off with this recursion call, and you can again try out the fourth index, and you'll not be able to pick up anything because on the fourth index there is a 2 and your target value is 1. So again this recursion call will also not be a valid recursion call, so you cannot call this recursion as the target is lesser than the array index that you're calling for. So this recursion call is over. So now you come across to this recursion call which is left out to be executed. So you're currently at the fourth index and you have a target that is 2 which is left out. So your data structure has 2. So it's looking for a second element, and you're at the fourth index. So you can pick up the fourth index. So the fourth index has a 2. And if you decide to pick it up, your combination will become 2 comma 2. So what I can say is when you have picked up the fourth combination, you go to the next index that is 5 and you have picked that out. Yes, you have picked that out. So I can say my target value again try out the fourth index, and you'll not be able to pick up anything because on the fourth index there is a 2 and your target value is 1. So again this recursion call will also not be a valid recursion call, so you cannot call this recursion as the target is lesser than the array index that you're calling for. So this recursion call is over. So now you come across to this recursion call which is left out to be executed. So you're currently at the fourth index and you have a target that is 2 which is left out. So your data structure has 2. So it's looking for a second element, and you're at the fourth index. So you can pick up the fourth index. So the fourth index, this recursion call
So in this case, G is the goal node. So we will start at A, and then we will go to this particular left subtree that iterative deepening depth first search algorithm in artificial intelligence with a simple numerical example. This is the modified version of depth limited search algorithm, which is again a modified version of depth first search algorithm in artificial intelligence. I have discussed both depth first search algorithm as well as depth limited search algorithm in the previous videos. Link for those videos is given in the description below. To understand iterative deep link depth first search algorithm, first we will try to understand depth first search algorithm briefly. In DFS algorithm, we will start at the root node and then we will try to traverse the left side of that particular tree, and then if we get the root goal node, we will stop over there. Otherwise we will try to search the right side of that particular tree. The same process will be continued unless and until we will get the goal node here. So in this case, G is the goal node. So we will start at A, and then we will go to this particular left subtree, that is B. From this particular B, we will go to the left subtree again, that is D, because B is not a goal node. Now from this particular D, we will go to H. Now when you read this particular H, we don't have any further nodes here, so we will try to go back and then get the right subtree. To this particular D, we don't have any right subtree, so we will go to this particular B. We have a right subtree, so it will go to this particular E here. Now from this particular E, we will go to this particular I. Still we have not yet reached the goal node here, so we will go to this particular A. The right subtree is equivalent to C here. Now from C, we will go to this particular F. From F, we will go to this particular G in this case. So once you reach this particular goal node, we will stop here. So this is how the DFS algorithm works in this case. In iterative deepening depth first search algorithm, rather than going to this particular the leaf node to get this particular goal node, we will do one thing. We will put a restriction on this particular label in every iteration. For example, in iteration 0, we will consider that the label is equivalent to 0 in this case. That is, we will try to search the goal node only at this particular level in this case. So that is, the tree is considered only up to here, not below this particular thing. So if you consider only this much, we will reach this particular A. A is not a goal node, so we cannot get this particular goal node with respect to the level 0 here. So what we do is we will extend this particular level up to here, that is level 1. So we will consider only up to A, B, C here. Now again we will start at A. So when you start at this particular A, we will go to what is that called as B here, and from this particular B we cannot go beyond this particular level, because as I said earlier, it is iteration 1 and the level is equal to 1 over here. So it will try to search in the right hand side. We will go to this particular C here. Again, we haven't reached this particular goal node with respect to this iteration. Again here, that is level 1, so we will consider only up to A, B, C here. Now again we will start at A. So when you start at this particular A, we will go to what is that called as B here, and from this particular B we cannot go beyond this particular level, because as I said earlier, it is iteration 1 and the level is equal to 1 over here. So it will try to search in the right hand side. We will go to this particular C here. Again, we haven't reached this particular goal node with respect to this iteration. So what we do, we will increase the iteration here, 0 in this case. That is, we will try to search the goal node only at this particular level in this case. So that is, the tree is considered only up to here, not below this particular thing. So if you consider only this much, we will reach this particular A. A is not a goal node, so we cannot get this particular goal node with respect to the level 0 here. So what we do is we will extend this particular level up to here, that is level 1. So we will consider only up to A, B, C here. Now again we will start at A. So when you start at this particular A, we will go to what is that called as B here, and from this particular B we cannot go beyond this particular level, because as I said earlier, it is iteration 1 and the level is equal to 1 over here. So it will try to search in the right hand side. We will go to this particular C here. Again, we haven't reached this particular goal node with respect to this iteration. So what we do, we will increase the iteration in here. So the iteration in this case will become the 2 and the level is equal to 2 here. So up to here we will try to search in this case. So again we will start at A, it will go to B, and then from B to D. From D we will not go to this particular H, because we have already reached the level. So we will go back to this particular E now, and then from E we will not go to this particular I, we will come back to this particular C here. From C we will go to this particular F. From F we will come back to this particular G here. So in this case, A to B, B to D, D to E, E to C, C to F, and F to G. Now we have reached the goal node. So that is the final the path in this particular case. So in this case, what we did is we will start with level 0, and then we will try to search for the goal node. If we found it's quite good, otherwise we will increase this particular level, and then we will try to find the goal node. Again, if you find it, it's quite good. Otherwise we will go on increasing the levels unless and until we will get this particular goal node over here. So this is how the iterative deepening depth first search algorithm works. This is the modified version of depth limited search algorithm. In depth limited search algorithm, we will set one limit. Below that only we will try to search for the goal over there. I have discussed that particular algorithm in the previous video. Do follow that particular video to understand the depth limited search algorithm in artificial intelligence. So in this video, I have discussed the node that is closest to the goal node. Hence, welcome back. In this video, I will discuss greedy best first search algorithm in artificial intelligence with the help of simple solved example. This is the solved example number 1. Link for other example is given in the description below. Greedy best first search algorithm tries to expand the node that is closest to the goal node. Hence, it evaluates the node by using the heuristic function, that is f of n is always equivalent to h of n, where h of n is the estimated cost from
सब्सक्राइब टू नॉलेज गेट बाइट्स चैनल, जहां हम डिस्कस करते हैं कंप्यूटर साइंस रिलेटेड टॉपिक्स स्मॉल वीडियोस में। तो चलिए अभी बात करते हैं इन्फॉर्म सर्च या फिर ह्यूरिस्टिक सर्च एल्गोरिथम्स या सर्च अप्रोचेस की या सर्च स्ट्रेटेजीज की। तो बल्कि कॉमन सेंस में अगर आपको समझाऊं तो आइडिया क्या है? आइडिया ये है कि ऐसा नहीं है कि आपके उसको इन्फॉर्मेशन कोई क्लू नहीं है। फॉर एग्जाम्पल एक तरीका तो है कि जंगल में हम कोई चीज़ ढूंढ रहे हैं और हमारे पास कोई भी क्लू नहीं है, रैंडमली चारों तरफ देख रहे हैं। एक है कि फॉर एग्जाम्पल सपोज आप आगरा गए और अब आपको जाना है ताजमहल में, भी आपका नेट नहीं चल रहा और आज के टाइम की बात करें जीपीएस है बट वो काम नहीं कर रहा, गूगल मैप्स काम नहीं कर रहा, अब क्या करेंगे? यू कैन आस्क टू सम पर्सन, और हो सकता है उसको एग्जैक्ट रास्ता ना पता हो, बट ये जरूर हो सकता है कि वो आपको अंदाजा बता दे कि कुछ इधर से आप चले जाओ। ऑब्वियसली अगर ज्यादातर 100 में से 90 बार अगर आप उस इन्फॉर्मेशन को यूज करेंगे तो आपको पूरा सिटी एक्सप्लोर नहीं करना पड़ेगा, रिलेटिवली आप जल्दी पहुंच जाएंगे। यहां पर भी कई बार हमारे पास ऐसे क्लू, ऐसे इन्फॉर्मेशन हो सकते हैं जिसको हम बोलते हैं ह्यूरिस्टिक्स या इन्फॉर्म सर्च, जिनका इस्तेमाल करके बजाय इसके कि प्रॉब्लम को ओवरऑल एक्सप्लोर किया जाए, हम रिलेटिवली कम टाइम के अंदर सॉल्यूशन तक पहुंचते हैं। ये सर्च हमेशा ऑप्टिमल सॉल्यूशन जनरेट करें वो जरूरी नहीं है, क्योंकि इन जितने भी अप्रोचेस हम यहाँ यूज करेंगे, बेस्ट फर्स्ट सर्च है, ए स्टार है, ए स्टार है, उन सबकी सक्सेस हम माने या ना माने बहुत हेविली डिपेंड करती है कि ह्यूरिस्टिक कैसी थी, इन्फॉर्मेशन कैसी थी। कभी कभी कोई आदमी बहुत एग्जैक्ट बता सकता है कि आगे जाओ, एक लेफ्ट होगा और वहां से जाओगे, एग्जैक्ट रास्ता आपको मिल जाएगा। और हो सकता है कोई आदमी खुद भी कंफ्यूज और आपको डबल कंफ्यूज कर दे, वो बोले कुछ आपको कुछ समझ आए, उल्टा ज्यादा टाइम लग गया, वरना आप खुद तो उसी रास्ते जा ही रहे थे, ऐसा हो भी सकता है। तो अगर ह्यूरिस्टिक क्वालिटी अच्छी नहीं होगी तो आपका सर्च टाइम ज्यादा भी हो सकता है। तो इन जनरल दे जनरेट गुड सॉल्यूशन, समटाइम्स ऑप्टिमल, समटाइम क्वाइट क्लोज टू ऑप्टिमल, बट जितने टाइम में जनरेट करते हैं बड़ा फैसिनेटिंग है। कम मेमोरी लगती है, कम स्पेस लगता है, क्योंकि पूरी प्रॉब्लम या पूरे पाथ के हर रास्ते एक्सप्लोर नहीं करते। सो आई विल गो वन बाय वन। Heuristic search strategies are like a smart search methods that uses special knowledges or hints to find solution more effectively. तो वो hints और information use करते हैं एक effective solution निकालने के लिए। It is similar to when we use our intuition or common sense to solve the problem. हालांकि ये थोड़ा सा ज्यादा हो गया, but still कभी कभी हम कुछ कॉमन सेंस या इंट्यूशन भी यूज कर सकते हैं, बट यहाँ इंट्यूशन यूज करेंगे, हमारे पास कुछ ह्यूरिस्टिक मेथड होगा जिसका इस्तेमाल करेंगे जिस इन्फॉर्मेशन का। अब यहाँ पर जो फ्लैग बियरर है, जो पहला हमारा एल्गोरिथम है, दैट इज कॉल्ड बेस्ट फर्स्ट सर्च। आई विल कम टू द थ्योरी पार्ट, लेकिन पहले एक न्यूमेरिकल डायरेक्टली सॉल्व कर लेते हैं, कहानी खत्म पैसा जम। तो क्वेश्चन आपको समझ आ गया तो सारी चीज आप ऑटोमेटिकली समझ जाओगे। नाउ लुक एट दिस, दिस इज अ अनडायरेक्टेड बट वेटेड ग्राफ, और हर नोड से या हर एज के ऊपर आप एक कॉस्ट देख रहे हैं जो कि रिप्रेजेंट करता है, फॉर एग्जांपल बी से ई तक जाने की कॉस्ट 14 है, सी से ई तक आने की कॉस्ट 7 है, ई से एस तक जाने की कॉस्ट 8 है, समथिंग लाइक दिस। यस, अब हमारा काम है ए से जी तक जाना। अगर जो कॉस्ट हमें एग्जैक्टली गिवन है, अगर हम उन वैल्यूज का इस्तेमाल करें तो बहुत सारे एल्गोरिथम ऑलरेडी हैं हमारे पास, जैसे डिजकास्ट्रा है, बेलमैन फोर्ड है, जो सिंगल सोर्स शॉर्टेस्ट पाथ, एक सोर्स से एक गोल तक जाने का रास्ता आपको बताते हैं। बट इस बार हम इन वैल्यूज को यूज नहीं करते। तो यहां पर क्योंकि प्रॉब्लम क्या है ना, समझो, आप बोलोगे क्यों नहीं यूज कर रहे? फर्स्ट स्टेज पे देख के आप कभी नहीं बता सकते कि 6 से आगे जाके बेटर रास्ता आएगा, 13 से आएगा कि 10 से आएगा। तो बेसिकली ऑप्टिमैलिटी जनरेट करने के लिए हमें पूरा ग्राफ एक्सप्लोर करना पड़ता है, और तब धीरे 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 हम आगे जाते हैं, देन समहाउ वी जनरेट ऑप्टिमल सॉल्यूशन। प्रॉब्लम ऑप्टिमैलिटी की नहीं है, प्रॉब्लम टाइम की। यार बहुत टाइम लग रहा है इसमें, कुछ सस्ता तरीका बताओ। तो दे यू सी, हमारे पास इस बार एक नया फंक्शन है जिसको हम बोल रहे हैं ह्यूरिस्टिक फंक्शन। अभी ह्यूरिस्टिक फंक्शन क्या है? हमें अंदाजा है, दोबारा समझना, ये एग्जैक्ट वैल्यू नहीं है, और हमें ऐसा अंदाजा है कि ए से गोल तक जाने की कॉस्ट 39 है। हमें ऐसा लग रहा है, हमें ऐसा पता है, कैसे पता है वो भी बताऊंगा। हमें ऐसा लग रहा है कि डी से गोल तक जाने की कॉस्ट 34 है, या एच से गोल तक जाने की कॉस्ट 9 है। ये सेम कॉस्ट से मैच हो भी सकता है, नहीं भी हो सकता है, ये आगे बात करेंगे। ये ओवर एस्टिमेट भी कर सकता है, अंडर एस्टिमेट भी कर सकता है। हो सकता है जो बोल रहा हूं एक्चुअल कॉस्ट बाद में उससे कम निकले, हो सकता है जो बोल रहा हूं एक्चुअल कॉस्ट बाद में उससे ज्यादा निकले, बट वो बात की बात है। फिलहाल इस क्वेश्चन के अंदर हम क्या करने वाले हैं, हम इन एग्जैक्ट वैल्यू को यूज करेंगे ही नहीं, हम पूरा गेम सिर्फ ह्यूरिस्टिक पे ही खेलेंगे। और यही गेम है बेस्ट फर्स्ट सर्च का। बेस्ट फर्स्ट सर्च सिर्फ एक ही चीज को वैल्यू करता है, वो है आपका एस्टिमेशन। आपके ग्राफ के वैल्यूज की एग्जैक्ट कॉस्ट की उनकी कोई वैल्यू नहीं है। अब बीच में क्वेश्चन की सर ये आया कहां से, तो इसकी अलग अलग मैथमेटिक्स हो सकती है, जैसे ग्राफ के केस में एक कॉमन सेंस आइडिया है जिसको बोलते हैं स्ट्रेट लाइन डिस्टेंस। इस तरह से आप इमेजिन कर लो कि हमने मैप के ऊपर स्केल रख के स्ट्रेट लाइन डिस्टेंस कैलकुलेट कर लिया और वो काइंड ऑफ हमारा ह्यूरिस्टिक फंक्शन की तरह काम करेगा। वो ऑब्वियसली अगर मैं बी से जी तक जाऊंगा तो स्ट्रेट लाइन डिस्टेंस कम होगा, है ना, थोड़ा सा मेरे को घूम घूम के जाना पड़ेगा, जैसे मैप्स में भी होता है। अगर दिल्ली से बॉम्बे की आप डायरेक्ट लाइन ड्रॉ करोगे तो ऑब्वियसली कम निकलेगा, बट ट्रेन एकदम स्ट्रेट लाइन में तो चलेगी नहीं, कभी जयपुर जाएगी, कभी कोटा जाएगी, कभी सूरत जाएगी, तो थोड़ा इसको उधर उधर होकर जाना पड़ेगा, तो थोड़ा ज्यादा निकलेगा, बट मोटा मोटा अंदाजा आपको पता लगेगा। तो अब ये कैसे काम करेगा ये देखते हैं। बहुत मजेदार अप्रोच है, एक बार आइडिया आपको समझ आना तो एआई में कैसे हम काम करते हैं और कैसे अपना टाइम बचाते हैं सब सीखने का मौका मिलेगा। सो मैं यहां से शुरू करता हूं। हमारा सोर्स नोड है ए, है ना। अब आप मुझे बताओ ए से बाहर जाने के कितने रास्ते हैं? सर ए से बाहर जाने के 3 रास्ते हैं। एक रास्ता है ए से डी का, एक रास्ता है ए से सी, है ना, इधर आ जाता हूं मैं, और एक रास्ता है ए से बी। अब अगर हम कोई नॉर्मल एल्गोरिथम यूज कर रहे होते तो अप्रोच होती कि सर डी का कॉस्ट क्या है, इसका कॉस्ट 6 है, इसका कॉस्ट 13 है और इसका कॉस्ट है 10, ऐसे सोचते। इस बार ऐसे नहीं सोचना, हमें देखना है ए का ह्यूरिस्टिक कॉस्ट कितना था, ये लिख लो चाहे तो सिंबॉलिकली 39 था। अभी बताओ डी, सी और बी का ह्यूरिस्टिक कॉस्ट क्या है। तो डी से अगर डेस्टिनेशन पे पहुंचना है तो डी का ह्यूरिस्टिक कॉस्ट है 3434। हमें एग्जैक्ट नहीं पता बट हमारा अंदाजा है। सी से गोल का कॉस्ट कितना है? सी से गोल का कॉस्ट है 2424। और बी से गोल का कॉस्ट कितना है? बी से कॉस्ट है 3131। अब बताओ इन तीनों में सबसे प्रॉमिसिंग कौन है? सर इन तीनों में सबसे बढ़िया तो सी लग रहा है। फिलहाल हम इस बात को इग्नोर कर रहे हैं कि ए से डी, ए से सी या ए से बी आने में कितना खर्चा हुआ, भूल जाओ उस बात को। ये बताओ सबसे आसान क्या लग रहा है? ये वाला लग रहा है। हम बाकी दो पाथ को फिलहाल एक्सप्लोर भी नहीं कर रहे और बस इसको फाइनल मान के आगे चलने लगेंगे। तो हम प्योर अंदाजे पे खेल रहे हैं। ये मैंने ऐसा भी नहीं है कि लोकल ऑप्टिमा देख के फिर ग्लोबल ऑप्टिमा की तरफ चल रहे, वो नहीं है ये। चलो सी से आगे जाने के रास्ते बताओ। सर सी से आगे जाने के 2 रास्ते हैं, एक रास्ता है वाया एफ और एक रास्ता है वाया ई, ऐसे ही है ना, ठीक है। अब जरा एफ का फिर दोबारा सी से एफ तक, अच्छा मैंने लिखा नहीं कुछ भी, मान लो लेट मी से 5, सी से एफ या सी से ई तक जाने के लिए एग्जैक्ट कितना रास्ता लगा उसकी कोई वैल्यू ही नहीं है, भूल जाओ उस बात को, एस्टिमेशन का गेम है। तो बताओ एफ से गोल का एस्टिमेशन कितना है? एफ से गोल का एस्टिमेशन है 1616 और ई से गोल का एस्टिमेशन है 1818। बताओ दोनों में कम कौन है? सर दोनों में कम तो एफ है, बस एफ को फाइनल मानो फिलहाल के लिए, फिर आगे बढ़े, ऐसे चलना है। एफ को मान के आगे बढ़ोगे तो एफ के आगे तो आई थिंक वी डोंट हैव मल्टीपल ऑप्शंस, सो एफ से आगे जाने का एक ही रास्ता है विच इज लाइक, अच्छा एफ से तो हम डायरेक्टली गोल पे जा रहे हैं ना, जी इज द गोल ओनली, तो एफ से आप डायरेक्टली पहुंचे और गोल का ह्यूरिस्टिक देखोगे दिस इज काइंड ऑफ 0 बिकॉज गोल तो गोल है, वहीं तो पहुंचना था। तो हमारा रास्ता क्या हुआ जो बेस्ट फर्स्ट सर्च एल्गोरिथम हमें रिटर्न करेगा? इट इज ए टू सी एंड देन एफ एंड जी। तो ए से सी होते हुए एफ होते हुए जी तक आप पहुंचेंगे, ये इसकी पूरी मैथ है। क्या ये हर बार ऑप्टिमल सॉल्यूशन जनरेट करेगा? इस बात की कोई गारंटी नहीं है, हो भी सकता है, हो सकता है जैसे हम बोलते हैं आमतौर पर इट्स अ गुड सॉल्यूशन, तो इट्स क्लोज टू ऑप्टिमल, बट जितने कम टाइम में करता है ना वो आमतौर पे फिनोमिनल है, बिकॉज जैसे पूरी टेंशन ही नहीं ले रहा भाई, इसकी वैल्यू को देख ही नहीं रहा, ह्यूरिस्टिक पे पूरा गेम खेल रहा है। दिस इज द आइडिया। आई थिंक आपको इस एग्जांपल से पूरी अप्रोच तो समझ आ गई होगी बेस्ट फर्स्ट सर्च की। अब मैं थोड़ा सा थ्योरेटिकल पॉइंट पढ़ लेता हूं ताकि एग्जाम में आपको आंसर लिखने में आसानी हो। सो best first search algorithm which explore the graph by expanding the most promising node choosing according to specific rule, और ये specific rule क्या है? वही हमारा heuristic function। तो जो सबसे promising लगता है उसको चूज करते हैं, उसको हम बोलते हैं बेस्ट फर्स्ट, बिकॉज इट greedily chooses the node that seems most promising according to the heuristic। तो मजे की बात है जो आम एल्गोरिथम है जैसे डिजकास्ट्रा, बेलमैन फोर्ड, जो हम एल्गोरिथम सब्जेक्ट्स में पढ़ते हैं वो सच में प्रॉमिसिंग होते हैं, बट यहाँ पे वो बाद में प्रॉमिसिंग निकले इस बात की भी गारंटी नहीं, बिकॉज इट सीम्स टू बी मोस्ट प्रॉमिसिंग, बट अगेन क्योंकि कम टाइम में तो अच्छा आंसर आता है, तो इट टेक्स द एडवांटेज ऑफ बीएफएस डीएफएस बोथ। और ये जो हमारा जिसके ऊपर पूरा गेम चला है एच ऑफ एन। सो व्हाट इज एच ऑफ एन? एस्टिमेट द कॉस्ट ऑफ द चीपेस्ट पाथ फ्रॉम द स्टेट एट अ नोड एन टू द गोल स्टेट। तो अगर कोई मेरा स्टेट है एन, वहां से कोई गोल स्टेट में मेरे को जाना है जी, तो यहाँ से गोल तक जाने का कॉस्ट एच एन है। हम यहाँ तक कैसे पहुंचे इस बात की कोई वैल्यू नहीं है, फिलहाल जो सबसे प्रॉमिसिंग एच एन है उसको लेके हम आगे बढ़ते हैं, जो एग्जाम्पल में आपने देख भी लिया। दैट इज अ काइंड काइंड ऑफ एल्गोरिथम जो चाहे तो आप ऑब्जर्व कर सकते हैं, यू कैन राइट इट डाउन, बट आई डोंट थिंक ज्यादातर केस में एल्गोरिथम आपको एग्जाम में लिखने के लिए बोलते हैं, स्पेसिफिकली एग्जांपल के साथ पूरा गेम बनाओगे तो मामला सेट हो जाएगा। एडवांटेज की बात करूं तो जैसा हमने समझा कि पूरा का पूरा एक्सप्लोर किए बिना जल्दी से क्वाइट क्लोज टू ऑप्टिमल सॉल्यूशन निकालता है। मेमोरी रिक्वायरमेंट भी बहुत ज्यादा नहीं है, कैलकुलेशन बहुत सिंपल है, पुराना कहां तक आ गया उसकी क्या कुछ देख ही नहीं रहा भाई, सिर्फ एस्टिमेशन पर कंपेयर कर रहा, आंसर निकाल रहा, कहीं प्लस माइनस डिवाइड मल्टीप्लाई किया ही नहीं हमने। क्या ये कंप्लीट है? तो अगर डायरेक्टेड ग्राफ पे डिस्कस करते हैं तो कभी कभी इस तरह के केस हो सकते हैं कि भाई साहब लूप में फंस जाए, कंप्लीट नहीं है। ऑप्टिमैलिटी की मैं पहले ही बात कर चुका हूं, इट गिव गुड सॉल्यूशन, सम टाइम इट मे गिव ऑप्टिमल सॉल्यूशन, बट दैट इज ऑब्वियसली नॉट गारंटीड। कभी कभी ये खराब आंसर कर सकता है, क्योंकि पूरा गेम ह्यूरिस्टिक फंक्शन पे डिपेंड करता है, वो अगर खराब है तो सॉल्यूशन भी खराब होगा। टाइम कॉम्प्लेक्सिटी, अब देखो जब हम वर्स्ट ऑफ द वर्स्ट सिनेरियो की बात करते हैं तो समहाउ इट मैचेस विद बीएफएस एंड डीएफएस, सो इट्स लाइक ऑर्डर ऑफ बी रेज टू पार्टी, वेयर अगेन बी इज द ब्रांचिंग फैक्टर, किसी नोड के कितने चिल्ड्रन एंड डी इज द डेप्थ, है ना। बट फॉर अ मैटर ऑफ फैक्ट ये नॉर्मली हम टच नहीं करते। प्रैक्टिकल केसेस में इसकी टाइम कॉम्प्लेक्सिटी बहुत कम होती है रिलेटेड टू बीएफएस एंड डीएफएस, क्योंकि हम पूरा ग्राफ एक्सप्लोर ही नहीं कर रहे, तो ना मेमोरी लगेगी इतनी, ना रिलेटिवली इतना टाइम लगेगा, है ना। ये इसकी कहानी है। एंड नाउ द नेक्स्ट आइडिया इज ए स्टार एल्गोरिथम। तो ए स्टार बोल सकते हैं बीएफ जो हमारा बेस्ट फर्स्ट था, थोड़ा सा ज्यादा आवारा अल्लड़ किस्म का है, बोल सकते हैं। ना मेमोरी लगेगी इतनी, ना रिलेटिवली इतना टाइम लगेगा, है ना। ये इसकी कहानी है। एंड नाउ द नेक्स्ट आइडिया इज ए स्टार एल्गोरिथम। तो ए स्टार बोल सकते हैं बीएफ जो हमारा बेस्ट फर्स्ट था, थोड़ा सा ज्यादा आवारा अल्लड़ किस्म का है। ए स्टार उसको थोड़ा बैलेंस आउट करता है। और ए स्टार जो हमारे जनरल एल्गोरिदम है, जैसे डिस्कास्टर बेलमनफोर्ड जिनकी मैं बात कर रहा हूँ, जो एग्जैक्ट एकदम डिस्टेंस एक एक देखते हैं, और जो हमारा बेस्ट फर्स्ट सर्च है जो सिर्फ एस्टिमेशन देखता है, दोनों का मिक्सचर है। तो अगर मैं आपको आइडिया यहाँ पर बताऊँ, लुक एट दिस, कितने शानदार तरीके से इस बात को समझाने की कोशिश कर रहा है। अगर हमें सोर्स स्टेशन से गोल तक पहुंचना है और हम किसी स्टेशन एन पे फंक्शन एफ ऑफ एन कैलकुलेट कर रहे हैं, तो एफ ऑफ एन सिर्फ एच एन का मतलब नहीं है जो आगे की हमारी एस्टिमेशन कॉस्ट है। इस बार हम ये भी देखेंगे कि एच एन एन तक हम कितने कॉस्ट में पहुंचे, तो दोनों चीज वैल्यू करेगा। तो मैं देखूंगा मैं एग्जैक्टली कितना खर्चा किया, ये अंदाजा नहीं है जीएन, ये तो ग्राफ पे जो लिखा हुआ उसको भी मैं यूज कर रहा हूँ। एग्जैक्टली मैंने कितना खर्चा यहां तक पहुंचने के लिए, हाँ, लेकिन इसके आगे जो भी एक्सप्लोर नहीं किया वहां पे मैं वही एच एन यानी कि एस्टिमेशन यूज करूंगा। तो चीजों को बैलेंस आउट करता है, थोड़ी प्रैक्टिकलिटी, थोड़ा अंदाजा। तो इन जनरल थोड़ा कॉम्प्लेक्स जरूर होगा, बट वी कैन एक्सपेक्ट कि ये बेटर सॉल्यूशन जनरेट कर देगा मोस्ट ऑफ द टाइम, इवन टू बेस्ट फर्स्ट सर्च। टाइम लगेगा, दिमाग लगेगा, देखते हैं कैसे। पढ़ता हूँ। So A star search is an informed search algorithm that combines the advantages of both uniform cost search and the greedy best first search. It evaluates node based on a combination of the cost of path from the starting node to the node, जो exactly cost है, and then to the node, and then an estimated heuristic function that estimates the cost to reach the goal from the current node. तो दोनों को जब हम मिला के यूज करते हैं, this is the exact cost, this is the heuristic function, तो वैल्यू आती है। कैसे आती है, एक एग्जांपल ले लेते हैं और इस पे काम करते हैं। तो लुक एट दिस, ये एक ग्राफ हमारे पास है और यहाँ पर और ए स्टार, ये इसकी कहानी है। एंड नाउ द नेक्स्ट आइडिया इज ए स्टार एल्गोरिथम। तो ए स्टार बोल सकते हैं बीएफ, जो हमारा बेस्ट फर्स्ट सर्च था, थोड़ा सा ज्यादा आवारा अल्लड़ किस्म का है। ए स्टार उसको थोड़ा बैलेंस आउट करता है। और ए स्टार जो हमारे जनरल एल्गोरिदम है, जैसे डिस्कास्टर बेलमैनफोर्ड जिनकी मैं बात कर रहा हूं, जो एग्जैक्ट एकदम डिस्टेंस एक एक देखते हैं, और जो हमारा बेस्ट फर्स्ट सर्च है जो सिर्फ एस्टिमेशन देखता है, दोनों का मिक्सचर है। तो अगर मैं आपको आइडिया यहां पर बताऊं, लुक एट दिस, कितने शानदार तरीके से इस बात को समझाने की कोशिश कर रहा है। अगर हमें सोर्स स्टेशन से गोल तक पहुंचना है और हम किसी स्टेशन एन पे फंक्शन एफ ऑफ एन कैलकुलेट कर रहे हैं, तो एफ ऑफ एन सिर्फ एच एन का मतलब नहीं है जो आगे की हमारी एस्टिमेशन कॉस्ट है। इस बार हम ये भी देखेंगे कि एच एन एन तक हम कितने कॉस्ट में पहुंचे। तो दोनों चीज वैल्यू करेगा। तो मैं देखूंगा मैं एग्जैक्टली कितना खर्चा किया, ये अंदाजा नहीं है जीएन, ये तो ग्राफ पे जो लिखा हुआ उसको भी मैं यूज कर रहा हूं। एग्जैक्टली मैंने कितना खर्चा यहां तक पहुंचने के लिए। हाँ, लेकिन इसके आगे जो भी एक्सप्लोर नहीं किया वहां पे मैं वही एचएन यानी कि एस्टिमेशन यूज करूंगा। तो चीजों को बैलेंस आउट करता है। थोड़ी प्रैक्टिकलिटी, थोड़ा अंदाजा, तो इन जनरल थोड़ा कॉम्प्लेक्स जरूर होगा, बट वी कैन एक्सपेक्ट कि बेटर सॉल्यूशन जनरेट कर देगा मोस्ट ऑफ द टाइम, इवन टू बेस्ट फर्स्ट सर्च। टाइम लगेगा, दिमाग लगेगा, देखते हैं कैसे। पढ़ता हूं। सो ए स्टार सर्च इज एन इन्फॉर्म सर्च एल्गोरिथम that combines the advantages of both uniform cost search and the greedy best first search. It evaluates node based on a combination of the cost of path from the starting node to the node, जो exactly cost है, and then to the node, and then an estimated heuristic function that estimates the cost to reach the goal from the current node. तो दोनों को जब हम मिला के यूज करते हैं, this is the exact cost, this is the heuristic function, तो वैल्यू आती है। कैसे आती है, एक एग्जांपल ले लेते हैं और इस पे काम करते हैं। तो लुक एट दिस, ये एक ग्राफ हमारे पास है और यहाँ पर आप नोटिस करें क्या है, एग्जैक्ट कॉस्टिंग भी लिखी हुई है हर एक एज के ऊपर, है ना। और ये जो ऑरेंज कलर से आपको नंबर नजर आ रहे हैं, ये ह्यूरिस्टिक कॉस्ट ऑब्वियसली जेड पर नहीं लिखा बिकॉज उसका ह्यूरिस्टिक कॉस्ट 0 है। हमें ए से जेड तक जाने का रास्ता ढूंढना है। अब कैसे ढूंढेंगे, आइए एक एक करके शुरू करते हैं। तो सबसे पहले नोटिस करिए, शुरुआत तो स्मॉल में ही लिखूँ मैं, यहाँ स्मॉल केस लिखा हुआ है, ओके। तो शुरुआत तो मैं ए से ही करनी है, तो मैं ए से शुरू करूंगा। मुझे बताइए ए से आगे जाने के कितने रास्ते हैं। सर ए से आगे जाने के 2 रास्ते हैं, या तो वाया बी जा सकते हैं या तो वाया सी जा सकते हैं, ठीक है। अब ध्यान से देखना ये कैसे कैलकुलेट करेंगे। अब हमें बी और सी के लिए एफ एन कैलकुलेट करना है, तो मैं पूरा करके दिखाता हूँ। व्हाट इज एफ ऑफ बी। एफ ऑफ बी 2 बात पे डिपेंड करेगा। पहले तो जी ऑफ बी, यानी कि बी तक पहुंचने का, पूरी बात लिखूं, डिपेंड करेगा जी ऑफ बी पे और एच ऑफ बी पे, है ना। तो जी ऑफ बी, बी तक पहुंचने की कॉस्ट जो कि कितनी है, एग्जैक्टली 4, और प्लस एच ऑफ बी यानी कि ह्यूरिस्टिक वैल्यू ऑफ बी जो अंदाजा है बी से जेड तक पहुंचाने का, जिसकी कॉस्ट है 12। तो अब यहाँ पर हमारे पास जो ओवरऑल कॉस्ट आ रही है वो आ रही है 1616। इसमें एग्जैक्ट भी और अंदाजा भी है। जब हम सी की बात करते हैं तो फिर से सेम फंक्शन यूज करिए। बताइए व्हाट इज एफ ऑफ सी। ये भी 2 बार पे जी तक ह्यूरिस्टिक फंक्शन, इसको भी डेड नहीं मान रहे, लेकिन फिलहाल ऑप्टिमल नीचे वाला है तो इसको हमने आगे एक्सप्लोर करना शुरू कर दिया। तो यहां तक का तो रास्ता हमारा फिक्स हो गया। यस, अब इसके आगे फर्दर आप देख सकते हैं 2 रास्ते हैं, या तो वाया ई आप जा सकते हैं या तो वाया डी जा सकते हैं। आइए इसको एक्सप्लोर करते हैं। तो अब क्या करेंगे देखें। सो अगर मैं डी की बात करूं तो अब मेरे को क्या कैलकुलेट करना है, मेरे को कैलकुलेट, यहाँ लिखो, मेरे को कैलकुलेट करना है पहले तो एफ ऑफ डी, एक रास्ता ऐसे, और एक हमें कैलकुलेट करना है एफ ऑफ ई। तो जब हम एफ ऑफ डी कैलकुलेट करेंगे तो अगेन 2 चीजें, एफ ऑफ डी पहले g ऑफ d कैलकुलेट करेंगे और फिर h ऑफ d कैलकुलेट करेंगे। नाउ व्हाट इज g ऑफ d? d तक पहुंचने की एग्जैक्ट कॉस्ट, तो 7 3 + 7 एग्जैक्ट कॉस्ट है 10 एंड h ऑफ d यहाँ का ह्यूरिस्टिक कॉस्ट है 6। तो ऐसा लग रहा है कि इससे अगर आगे गए तो टोटल कॉस्टिंग 16 आएगी, जबकि अगर e ई की बात करें तो ई तक का एग्जैक्ट कॉस्ट कितना है? तो अगेन मैं पूरा लिखूं क्या? ई जी एंड देन एच ऑफ ई। तो ई तक पहुंचने का एग्जैक्ट कॉस्ट है 3 3 + 10, सो दिस इज 1 3 13 और इसका ई का ह्यूरिस्टिक कॉस्ट है 4, सो दिस इज 17। तो अगेन आप देख सकते हैं दोनों में बेटर कॉस्ट क्या है। सो दोनों में बेटर कॉस्ट फिलहाल समझ आ रहा है 1 6 16 विच इज लाइक डी। तो अब हम लुक एट दिस, यहां तक आ गए, है ना। अच्छा, इसके आगे आप नोटिस करेंगे तो इसके आगे डी के बाद एक ही पास बात है 16। अच्छा, एक और पुरानी वैल्यू 16 है जिससे मैच कर रहा हूं, बट क्योंकि मेरा भी सेम है तो मैं इसके साथ आगे कंटिन्यू कर सकता हूं। अच्छा, यहाँ कैलकुलेट करने की जरूरत इसलिए नहीं क्योंकि एक ही चॉइस मेरे पास है, तो मान लेता हूँ यही रास्ता मैं चूज करके आगे जाऊंगा और उसके आगे भी कैलकुलेट करने की जरूरत नहीं क्योंकि अगेन एक ही चॉइस है ना। सो अगेन यही रास्ता मैं चूज करके आगे बढ़ूंगा। तो ये जो हमारा ह्यूरिस्टिक फंक्शन है, बताओ क्या टोटल कॉस्टिंग कौन सा रास्ता इसने चूज किया? इट इज लाइक 3 + 7 + 2 + 5, ठीक किया ना। 3 + 7 + 2 + 5, so this is like 10 and this is like 7, तो टोटल 17 वाला कॉस्ट वाला पाथ ही रिटर्न करेगा। क्या इससे बेटर कुछ रास्ता हो सकता था? एक बार खुद से देख ले। वैसे मेरे को तो पॉइंट ऑप्टिमल ये लग रहा है। अगर हम इधर से जाते तो हमको 18 मिलता, ऊपर से आते तो यहीं तक हमारा 16 हो चुका था, कोई मतलब नहीं है। 9 एंड ये सब ज्यादा आता, सो दिस इज द ऑप्टिमल पाथ। अच्छा, यहाँ जाके आप समझ रहे हैं मैं क्यों एक एक वैल्यू कैलकुलेट नहीं कर रहा? बिकॉज मेरे को पता ही है कि इधर से आगे बढ़ना है तो यही रास्ता होगा। तो दैट इज हाउ इट वर्क्स। तो मेरे ख्याल से जो गेम है ये मच बैलेंस्ड है, पहले से बहुत बेटर है, क्योंकि ये सिर्फ ह्यूरिस्टिक पे काम नहीं कर रहा है, ये एग्जैक्ट कॉस्टिंग भी देख रहा है जिस हिसाब से हम आगे बढ़ रहे हैं, है ना। तो दिस इज मच मच बेटर। तो नाउ इफ आई गो बैक टू द आइडिया, ये लॉजिक आपको समझा चुका हूँ, दैट इज द एग्जैक्ट एल्गोरिथम। अगेन जैसा मैं बोल रहा हूँ, इफ यू वांट आप एक बार इसको ऑब्जर्व कर सकते हो, 2 बार पढ़ना, 1 बार लिख के देखना, सो दैट एग्जाम में अगर पूछे तो बना बना के लिख के आओ। इसमें ध्यान रखना, जब भी एल्गोरिथम लिखने की बात है, इट इज नॉट लाइक कि सी प्रोग्राम लिखना है, जावा में प्रोग्राम लिखना है। अगर नेचुरल लैंग्वेज में लिखते हैं लेकिन बात समझ आ रही है तो दैट इज मोर देन सफिशिएंट। कंक्लूड करें इसको फटाफट। सो ए स्टार इज कंप्लीट इफ द सर्च स्पेस इज फाइनाइट एंड ह्यूरिस्टिक फंक्शन इज एडमिसिबल। तो आगे मैं इसकी बात दोबारा करूंगा, लेकिन इस बात का मतलब क्या है? पहले ऑब्वियसली सर्च स्पेस तो फाइनाइट होना चाहिए, इनफाइनाइट में तो कोई भी नहीं चलेगा। एडमिसिबल का मतलब ये है कि ह्यूरिस्टिक फंक्शन जो भी कॉस्ट बताएगा, जो एक्चुअल कॉस्ट है उससे हमेशा कम होना चाहिए, इसको बोलते हैं एडमिसिबल होना, है ना। ओवर एस्टिमेट अंडर एस्टिमेट वाली बात है, तो दिस इज लाइक अंडर एस्टिमेशन अगर आप करेंगे तो एस्टिमेशन एडमिसिबल होगा। तो मान लीजिए अगर एग्जैक्ट कॉस्ट किसी रास्ते की है 10, अब ह्यूरिस्टिक फंक्शन बोल सकता है 8 भी बोल सकता है 12 बोल सकता है, तो हमको 8 वाला चाहिए। अगर हर बार हम अंडर एस्टिमेट करते हैं तो एडमिसिबिलिटी आती है, इस बात को ध्यान रखना है ना। तो उस केस में ये बिल्कुल कंप्लीट होगा। ऑप्टिमल इफ द ह्यूरिस्टिक फंक्शन एडमिसिबल एंड कंसिस्टेंट, तो आगे जाके मैं इसकी फिर और डिटेल में थोड़ी बात करूंगा, लेकिन ये वही वाला पॉइंट है। तो यहाँ पर ये ऑप्टिमैलिटी की गारंटी दे रहा है विद दिस कंडीशन, जो भी हम एक्सप्लोर करेंगे अंडर एस्टिमेशन वाला पॉइंट, विच इज इंपॉर्टेंट पॉइंट। टाइम कॉम्प्लेक्सिटी, ए स्टार डिपेंड्स ऑन ह्यूरिस्टिक फंक्शन, ब्रांचिंग फैक्टर, स्ट्रक्चर ऑफ द सर्च, सो वर्स्ट केस अगेन। तो इन सब में आपको समझिए, पहली बात तो कोई एनालिसिस नहीं करना, कोई डिटेल एल्गोरिथम नहीं बताना, ऑब्वियसली पहले से बेटर होगा। बेस्ट फर्स्ट सर्च से थोड़ा सा ज्यादा कॉम्प्लेक्स होगा, लेकिन सॉल्यूशन और ज्यादा ऑप्टिमल भी आएगा, बट वर्स्ट केस में अगेन इट विल शूट अप टू ऑर्डर ऑफ बी रेज़ टू पावर डी, एंड सेम अप्लाइज विद द टाइम कॉम्प्लेक्सिटी। इवन इसकी जो स्पेस कॉम्प्लेक्सिटी है ये बेस्ट फर्स्ट सर्च से ज्यादा होगी, क्योंकि ज्यादा कैलकुलेशन इसको करनी पड़ेगी। अब एडमिसिबिलिटी वाला पॉइंट क्या, मैं एक एक करके पढ़ता हूँ, इंपॉर्टेंट है, कई बार ये इंडिपेंडेंटली पूछ लिया जाता है 5 नंबर में कि जरा ए स्टार की एडमिसिबिलिटी समझा दो क्या है। सो आई गो वन बाय वन। कंसिस्टेंसी एंड एडमिसिबिलिटी, the first condition we require optimality of h of n, that वो admissible होना चाहिए। the admissible heuristic is that which never overestimates, note this point। overestimate का मतलब अगेन जैसे मैंने बताया, एग्जैक्ट कॉस्ट बाद में अगर 8 निकल रही है, आप 6 बोल दो, लेकिन आप 9 मत बोलना, 12 मत बोलना, 15 मत बोलना, तो हमेशा कम बताना। to reach the goal, admissible heuristic by nature is optimistic because they think that the cost of solving a problem is less than the actual cost। तो हमेशा कम बताना, ज्यादा नहीं बताना। यस, तो जैसे स्ट्रेट लाइन डिस्टेंस मैंने वाली आपसे बात की थी, वो हमेशा एडमिसिबल होगा, क्योंकि स्ट्रेट लाइन में ट्रेवल करोगे तो उससे कम तो कुछ हो ही नहीं सकता, समथिंग लाइक दिस। ओके, एंड द सेकंड कंडीशन इज लाइक कंसिस्टेंसी। कंसिस्टेंसी का मतलब अगेन हमेशा ये, जैसे इसमें आप देखोगे, मैं एक बार एक्सप्लेन कर देता हूँ। A heuristic HN is consistent if every node n and every successor n dash of n generates an action A, and the estimated cost of reaching the goal from n is no greater than the step of getting n plus। अब n से एक तरीका था gn पे जाने का, एक तरीका है वाया n डैश होते हुए जाने का। तो दिस इज लाइक कॉमन सेंस बात कि अगर मैं वाया n होके जाऊंगा, अगर मैं वाया n होके जाऊंगा और यहां से होके जाऊंगा और मैं एडमिसिबल होना चाहता हूं, तो हमेशा ये जो कॉस्टिंग होगी इधर से घूम के जाने वाली, ये कॉस्टिंग या तो बराबर होगी या तो ज्यादा होगी। अगर ये चीज पे हम काम कर पा रहे हैं तो इसको हम क्या बोलते हैं, दैट इज कॉल्ड कंसिस्टेंसी। यस, सो एवरी नोड एंड एवरी सक्सेसर इंडेक्स इज ओवर जनरेटेड बाय n, द एस्टिमेटेड ऑफ रीचिंग अ गोल n is no greater than the step of getting n dash plus estimated goal of reaching goal from n dash। तो h of n dash अगर आप निकालेंगे एस्टिमेशन और कॉस्ट देखेंगे n से एक्शन a लेके n dash पे आने की, तो ये ओवरऑल मिला के अगर ज्यादा होगी तो ऑब्वियसली हम ज्यादा ही चले जाएंगे। अगर हम इधर से जाते हैं, भाई ये कंडीशन बोल रही है ये रास्ता ज्यादा है तो इधर से नहीं जाना, डायरेक्ट जाना, अगर ये कम होता तो अपन इधर से चले जाते हैं। यानी कि जैसे अगर आपको बताऊं, एल्गोरिथम वो टर्म होता है रिलैक्सेशन वाला, वो वाला आइडिया है, अगर बेटर तो रिलैक्स करेंगे वरना आगे बढ़ेंगे। नाउ अब अगला जो इसका वेरिएंट है विच इज कॉल्ड एओ स्टार एल्गोरिथम। हालांकि ऐसा नहीं है, जैसे बेस्ट फर्स्ट सर्च का हमने ए स्टार पढ़ा तो वो क्लियर कट इंप्रूवमेंट था टुवर्ड ओवर द बेस्ट फर्स्ट सर्च, यहाँ पर ऐसा नहीं है। तो ए स्टार एल्गोरिथम एक तरह से सोच सकते हैं सारे पॉसिबल केसेस कवर नहीं करता, कुछ खास तरह के ग्राफ होते हैं जिन पे ए स्टार काम नहीं करता, वहां पे एओ स्टार काम आता है। तो क्या अप्रोच, क्या आइडिया, एक एक करके आइए ऑब्जर्व करते हैं। लुक एट दिस। सो अभी बात करते हैं एओ स्टार एल्गोरिथम के बारे में। सो एओ स्टार एल्गोरिथम इज नॉट लाइक कि इट इज सेम एज ए स्टार, या उसका एक्सटेंशन नहीं है, थोड़ा सा प्रॉब्लम सेट डिफरेंट है जिसको ये डील कर सकता है, और ए स्टार जिस पे बात नहीं कर सकता। आइडिया क्या है, आई गो वन बाय वन। जो अभी तक हमने ए स्टार पढ़ा वो एक ही तरह के ग्राफ पे काम करता है जिसको बोलते हैं और ग्राफ, है ना। बट यहाँ पर जैसे मैं भी एग्जांपल्स आपको समझाता हूँ, एक और एज है हमारे पास जिसको बोलते हैं एंड है, जिसका मतलब क्या, जैसे मान लीजिए एक गोल है कि हम, हालांकि तो इट्स काइंड ऑफ अ फनी आइडिया कि हमारे पास एक फोन होना चाहिए। अब ये काम करने के दो तरीके हैं। पहला तरीका है विच इज लाइक अपने आप में कंप्लीट सॉल्यूशन है, यू कैन स्टील अ फोन। तो फोन चाहिए, किसी का चुरा लेते, बात खत्म हो गई, मिल गया फोन। या हम इसको दो सब प्रॉब्लम से ब्रेक कर लेते हैं। पहला प्रॉब्लम है कि हमें वी मस्ट अर्न मनी, क्योंकि ऑब्वियसली पैसा चाहिए फोन खरीदने के लिए, एंड देन वी कैन परचेज इट। बट देयर यू सी, जब हम इस तरह का कर्व यहाँ पर लगाते हैं तो इसको बोलते हैं एंड आर। अब आपको दोनों सॉल्व करने पड़ेंगे एंड दोनों का सॉल्यूशन बताएगा कि ओवरऑल गोल का क्या सॉल्यूशन है। तो इमेजिन करो फॉर एग्जांपल, स्टील करने का कॉस्ट था लेट मी से 4, हालांकि कोई लेजिटिमेट एग्जांपल नहीं है। अर्न करने की कॉस्टिंग है लेट मी से 10, और फिर उससे परचेज करने की कॉस्टिंग है 1, तो यहाँ की टोटल कॉस्ट है 11, यहाँ की टोटल कॉस्ट है 4। नाउ यू कैन कंपेयर दो। अब यहाँ बोल सकते हैं फॉर एग्जांपल दिस इज नॉट अ वैलिड सॉल्यूशन, तो हम यही वाला चूज करेंगे, बट इस तरह के एरिया में एओ स्टार काम आता है। सो द एंड और ग्राफ is useful for representing the solution of problems that can solve by decomposing them into a sets of smaller problem। छोटी प्रॉब्लम ब्रेक करना, for which must then be solved, उसका उसको सॉल्व करना है। तो ये जो आइडियाज था ये ए स्टार के अंदर पॉसिबल नहीं था। सो अगेन जैसा हम यूजुअली करते हैं, आई डायरेक्टली टेक एन ब्रांचिंग फैक्टर।